University of Minnesota, the physics force.
There they are. Look at all those kids out there. Woo! Welcome, welcome, welcome. Now, during some of the demonstrations we do, we call out each other's names. So the first thing we're going to do is introduce ourselves. And way over there on the left, that's Fred from Maple Grove. Let's hear it for Fred.
To my right here is a good friend of mine who is a retired teacher from Maple Grove, and his name is Jack.
Sam, thank you. Thank you very much. Thank you. Over here, this guy's name is John. He's a retired teacher from Mounds View. Only one who looks like a real scientist with his hair like that. He looks terrific. What do you think? Give it up for John.
Thank you. And this is my good friend Hank, the most powerful one in the crew. Hank.
And our University of Minnesota professor on the group, he's obviously the smartest person up here, and you can tell that because he'll tell you that himself. And in addition to that, his brain is starting to come out right there on the top of his head. He is so smart.
Thanks, Hank.
Give it up for Dan.
Okay, now we're going to have a little quiz. I'm going to count to 3, and I want you to yell out this person's name nice and loud. 1, 2, 3. Yeah, right here. 1, 2, 3.
Yeah.
Over here, 1, 2, 3.
John, right.
Over there, 1, 2, 3.
Ben.
Ben right here, 1, 2, 3.
Hey.
Right.
Okay.
Now, you're going to see some pretty remarkable things we can do with the laws of nature, and this shouldn't be confused with what you see at the movies and on TV. There they use tricks. Here we don't do tricks. We just use the laws of nature to do some pretty remarkable things, okay? Now, the demonstrations in our performance are for you to watch, to learn from, and to enjoy. Please do not attempt to do any of the demonstrations on your own. We are professionals and have taken the necessary safety precautions. Now, having said that, I'm going to ask y'all a question, and I want to hear a resounding yes. Are you ready for some physics? Yeah!
This is it. Here we go. Woo-hoo. The first topic for today is sound. The stuff that's wiggling your eardrums right now is sound. Now, most of you, I'm sure, are aware that sound is a wave. We don't see it because it's in the air, and the air, of course, being colorless, we don't see it. But we're all familiar with waves on bodies of water or even in a puddle when you throw in a stone. But, of course, the best wave there is the audience wave that you do at an athletic event when you're bored. So we need an audience wave here today. And the people down this side have a major responsibility, including up there in the balcony. When I give you the signal, I want you to start the wave. And we're going to send the wave across the auditorium over to the other side. And I'm sure, being good Minnesotans, you all know your part. Here we go. Are you ready? On 3. 1, 2, 3. Yes. No. It's got to be louder. So let's get into this one more time and loud now. Here we go. 1, 2, 3. Yeah! Now, think about it this way. Over there, we started a wave and we sent the wave across the room. We sent the energy across the room. That could have been a big bong on a drum that rippled the air. You played the role of the air. The air molecules wiggled all the way across to the other side of the room, which could wiggle somebody's eardrum and they would hear it. But one more thing. A true wave always leaves all the air molecules where they were after it passes. So you're all in the same seats, which is exactly the way it ought to work.
I can take this rubber hose and send a wave over to Fred, just like the wave that y'all sent across the room. I'm going to put a pulse in the top of it. And you see it go over there, just like y'all's wave did. Let me do it one more time, make it a little bit looser. You see that? Now, what did it do when it hit Jack? It came back, and it was on the bottom side. Watch that again. In fact, I can send one down on the bottom, and it bounces back. So Fred is that big guy over there that's made out of muscle and bone, and it bounces right off of it. In fact, I can send down a whole bunch of waves. They'll bounce off of Fred, and they'll come back and add and subtract from the ones I'm sending down. Let's do this. Now, where these waves subtract all the time are called nodes. And where they add all the time are called antinodes. Now, y'all already know all about these things because when you're out on the playground, you have a rope and you play a game where you jump in the antinode, right? What do you call that? Jump rope, huh? Let's play some jump rope.
I get to go first.
No, I get to go first.
What?
You went first last time.
I know I'm always first.
No, I get to go first this time.
No, I get to go
I'm going.
Now, how many times have you seen this happen out on the playground? Huh? It happens, doesn't it? But you know, this is a place where the physics we just saw can maybe come and help us out. Let's see if we can give Jack and Hank, both of them, their own antinode to jump in.
Well, let's
there
see.
you go.
And ouch. There we go. Get a little higher, Freddie. There we go. I can do this.
Woo!
Yeah, jumping rope inside antinode. Woo!
There you go. Antinode jumping.
Okay, now you just saw, we call that a standing wave. When you have the nodes and the antinodes in there, it's called a standing wave. You see what it looks like. Now we're going to see what it sounds like. What I have here is I have a Hoot tube, because it's a tube and because it hoots. And so what I'm going to do is I'm going to hold, it's got a piece of wire mesh right down here, and I'm going to heat like a screen. I'm going to heat that up with the flame that's right here on the stage, and we will see what happens after that. So we'll take and heat it up, should be enough, and then thank you. Thank you. So you got to say to yourself, why does it do that? And I got to say to you, if I were to hold you over that flame, you'd have some trouble too, wouldn't you?
Hey, Jack.
Yeah, what?
I got an idea. Put
do.
that tube over the burner again. Get it hot.
Okay, get the tube hot.
I like that sound.
Woo. You like that sound?
And let's see if we can't catch it.
Catch it.
Yeah.
Well,
let's,
okay.
Let's bag it. Pour it in here.
Don't spill.
There it is. It's in the bag. Let me pour it back in the tube.
Okay. Don't spill now.
I won't.
I tell you, Dr. Dan is a pretty smart guy, but he knows this isn't magic. You don't pour sound. The fact is that this down here, this wire mesh is hot. And as long as it's hot, then it moves air up through the tube. Because it heats the air, it gets less dense. So we have air moving through here, and then there's a kind of like a hissing sound down there in that screen. And then that is made up of all kinds of different frequencies, all kinds of different notes. And this tube, because of its length, picks up one of those frequencies and sets up a standing wave inside there, and so it makes that sound. Now when you tip it on its side, of course, like I did, then it stops because there isn't any air moving up through the tube, and it's still hot.
If that's true,
Yes.
heat it up again.
Heat it up one more time. Okay. All right, it's warm enough, I think.
Okay.
Yep.
Turn it. Now turn it on its side. I should be able to blow through it.
Why, yes.
Oh.
See? It's just that air moving through it.
understand.
Yeah, that's how it works. And so, yeah, isn't that kind of cool? That's called a Hoot tube. Whoa.
What if we try a different tube?
A different tube. Yeah, you see this one right here? You can see my ugly face through there, can you? You turn it over the other way, well, it's still ugly. I'm not looking any better because there's nothing in here. It's just an empty tube. But I do have a wire mesh on my fire down here, on my flame, because it's a Fisher burner, and it's making the hissing sound. And this will pick up one of those frequencies. Now you'll notice it's a different length, and so it'll be a different tune, or a different tone, but it should give us a sound. Oh yeah, see there? Makes it just like that. So Ah, yes. The big man with the big tube. Here we go. We're looking at a tube here.
Try this one.
This is a tube. Okay, let's see what that sound. Oh, yeah. 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 Sounds like something out of the jungle, doesn't it? Makes you want to go, wee, I'm on my way. In the jungle, the quiet jungle, the lion sleeps tonight. Yeah. That's a hoot tube and the standing waves and all like that.
Now, we were fooling around and we discovered that you could get standing waves inside a sewer pipe. So these are from the sewer pipe store. And if you take a carpet and you drop them, the walls vibrate, and for just a moment you get a standing wave. It's kind of a nice note. And of course, if you cut them different lengths, then you get different notes. So, yeah, get tuned up, guys, you know.
Okay.
All right, this next song our professor wrote. Dan wrote this just for you.
Here we go.
Think about, Dan. Think about.
Dr. Dan wrote that for us, all by himself.
All right, we're going to play one other tune, and if you know this tune, you could sing along. That'd be fun to have you sing along. Here we go.
Yes.
Great job, guys.
Way to go. You recognize it. Okay. Woo.
We've been looking at sound going through the air, and the air around us is like a big ocean. And we live at the bottom of that ocean. And that ocean has weight. If we could weigh the air that's on top of us, we'd find that there's 15 pounds on every square inch. And that weight, that air pressure, pushes in all directions. And that's why you don't feel it, because the air pressure inside of you is the same as the air pressure outside. But you can do some pretty remarkable things with air pressure. Now, one of the things that you do with air pressure is in a little toy pistol that has a dart that has a rubber cup on the end of it, and you call that rubber cup a suction cup. But how does that work? Well, it actually works with air pressure, and it's a toilet plunger, but we buy them for the show, and it's like a giant suction cup, and I'm going to show you how it works a little bit better. No. We buy these for the program, and so it's okay. It's clean. It's never been used.
Dan,
Yeah?
you got the wrong one. Remember, we put the red tag on the one we haven't used in the bathroom.
This one doesn't taste very good. I wonder if he did that on purpose. Much better. Now, what I've done is that I've pushed all the air out of there, and the rubber wants to come back to its original shape, but that means the air pressure inside is less than the air pressure outside. And so when I do that, it can't get away. Let's see what we can do with air pressure in the next several experiments, okay?
Air pressure.
Oh, what are you guys doing?
Air pressure.
No! That's not air pressure.
That's two.
No, it's not.
Wait, what?
No, no, wait a minute. Give me a chance. That's not air pressure.
What's the matter?
That's excess pressure because your diaphragm is pushing. So you're not using air pressure for
I
this.
have a way that I can show you. We can push on the projectile and use ordinary air pressure in the room. We've got a gadget over here, a device to help us out a bit. This is called a ping-pong cannon. And you can see why it's called a ping-pong cannon, because it shoots ping pong balls. Now, we've got this end open. I'm going to roll a ping pong ball down in here, and I'm going to put my mic in the end so you can hear it rolling down. It'll stop at the end. We've got a little valve down there to keep it from falling out the other end.
Oop, it's here.
There. Now, we're going to put some tape over each end, some 3M packaging tape, and seal up the ends so the air in here can't get out unless it goes through that little pump down there. We've got a pump here which is going to pump the air out. But that takes a long time, well, several minutes, to pump the air out of that. And while we're pumping the air out, Jack is going to come in and delight us with another demonstration, and then we'll come back in a moment and see how the pump is doing. Jack, would you help us out?
What we have here is another demonstration on air pressure, okay? We'll take this, this is just a rubber sheet with a shiny top chair. I want to put it on top of here, I want to push this down, and then it becomes a chair mover. Using air pressure, nothing but air pressure, isn't that cool? If I want to put it down here, I just let some air back in. See, what happens is I push the air out from between them, and as I do that, try to lift this off the top, it kind of like makes it want to bow upward, and it reduces the pressure between the sheet and the chair. The less pressure there, now the bigger air pressure outside pushes these two things together. And so we end up with the ability to move a chair from one place to another. Should you ever need to move your refrigerator, get a great big rubber sheet with a handle on it and move it from one place to another.
Now, while Jack did that, we were pumping down the tube, and we should have about 1/800th the amount of air in that tube that there was just a few moments ago. The rest of it has been pumped out. So we have a partial vacuum in here. Now, we're going to poke this dart. The dart cuts this way and this way at the same time so the air can rush in. It pushes the ping pong ball ahead of it while it rolls down toward the end, and it should be moving maybe 500-600 miles an hour. So it's very, very rapid. We don't have any idea what's going to happen when it hits the pop cans, but we're going to find out. Now, this is fairly loud, people, so you may want to stick a finger in your ear or both ears. I always use one ear anyway, and protect myself a bit. I'm going to fire the cannon, and the ping pong ball will roar down there 600 miles an hour and off towards Fred. Are you ready, people? Here we go. Now, Fred is picking up these cans. We got a big dent in this one and a smaller dent in this one. So they got a good kick when the ping pong ball rushed down. And now we've got a little surprise here for the people. I'm going to open up this can and we're going to see what's in here. The ping pong ball made it through one side of the can. Thanks, Fred. I got a device here called a bag-to-bird swing. It works on air pressure also. We've got two transparent discs here, and between the two transparent discs, there's a oversized rubber band laying there. So when I open this valve, air can rush in there. Right now I've pulled most of the air out and it just comes apart. But I'm going to take my powerful lungs and pull the air back out again. Now I'm coming up for air. I'm supposed to breathe some every week. Now, there's air pressure out here, the room air pressure here pushing this way, here pushing this way, but in between the two discs, very little air. So it's the effect of squeezing these two things together. Now, look at me carefully. I know this is dangerous, but look at me carefully. I weigh 285 pounds, more or less. And we're going to see if that is enough. Okay, bring it back down just a foot or so, Jay. Okay, I'm going to see if it'll be strong enough to hold me. The only thing holding me up is the air pressure on the top and the bottom.
How about a little ballet, John?
If we could have that down again. I'm going to turn the valve so air can rush in between the two discs again, and when I do, they just fall apart. The only thing holding me up there was some air pressure. Thank you.
We've got a similar set of plates like John had, and we've used a mechanical pump to pump the air all out of these. And in doing that, we have enough of the air out that if we wanted to, we could actually lift a small car with these. Now, we've got some people coming up to help us with this. And if I could get y'all to grab hold of this side. Okay? And y'all to grab hold of that side. Now, what we're going to do is to try to pull the plates apart, not try to pull one side, one team to the other side, okay? Just try and get these plates apart. And then when I ask y'all to quit, you'll need to stop, okay?
Right.
Okay. So let's see you pull the plates apart.
Now, just a minute. In order to make this historically correct, in Germany, the first time it was ever done, they used horses. So the crowd has to stamp their feet and whinny during this demonstration to make it historically significant. All right, let's hear a little whinny. All right, here we go.
Okay, let's pull them apart.
Whoa!
Okay, there we go. Whoa, Silver. Okay, now, to show you that it was just air pressure holding these together, I'm going to put my mic down here and open the valve, and when I do, you'll hear the air rush back in, and they just fall apart. Just air pressure. Woo! Thank you very much.
Thank you. Now, you've probably noticed we've been boiling water in this flask ever since the beginning of the show. This is just a bucket with some red water in it. We put a little dye in there so maybe you'll be able to see it. And the flask has a little bit of water in the bottom, which is boiling. And Jay is going to hand that up to me like so. Steam is still coming out the top. The water is still boiling because the flask itself is hot. I'm going to tip this over, put this long snout down in this bucket of cold water, and then we're going to watch and talk for a bit. Now, mostly up here is steam. The air gets driven out. We'll talk more about that in a minute. But as the steam turns back into water, the pressure in here goes down, and the outside pressure is now pushing the fluid up the stem. It's right about here, and it's going up. It's not very exciting. It's kind of like watching your money grow at current interest rates. But when the water gets to the top, the cold water is going to hit the steam, and then all of the steam is going to condense suddenly. That's going to happen right about now. And then things get more interesting. Isn't that pretty? Yeah. Now, you can tell there was little air in here. The steam pushed the air out because the air wouldn't condense. So everything up here condensed so that the water could fill the jug all the way to the top. Now, another way of saying that is, had you been in the jug, you think you have one problem, it's hot in there, but you have two problems. It's hot in there, and there's no air to breathe. So think about that during this next demo.
We've been boiling water inside this steel barrel for about 15 minutes. And as we boil the water inside there, all the air, the oxygen and the nitrogen and the stuff you need to breathe has been displaced with the steam. They're going to turn off the burners, and I'm going to put a plug in here to seal the barrel up. As I seal it up, what's inside the barrel? Just water and steam. Nothing else. No air, no oxygen, no nitrogen. That's it. Right now, the air pressure inside, the pressure inside, is the same as atmospheric pressure, but as that steam cools off, it'll condense back into water, and the pressure inside will become less than the pressure outside. It's going to become less. Oh, is it raining? You know, it doesn't rain often in Minnesota in January, but so as we cool this off, the pressure inside is dropping, the pressure outside is staying constant. So what's going to happen? Now, this is something where you don't want to take your eyes off of the barrel because it's not subtle. I've seen some of you teachers watching John Barber, and I know what a hunk y'all think he is.
What a beautiful man.
But don't. No, don't watch him. Only watch the barrel.
Watching the barrel.
Now, actually, nothing is ever going to happen. We're doing this experiment for the psychology department to see how long we can get a large audience to stare at a stupid white barrel.
Yep. One of two things could happen now, boy. And one of them's not very exciting. Watch the barrel.
Keep your eye on the barrel.
On the barrel. Watch the barrel. Watch the barrel. Watch the barrel. Tomorrow you'll give me all your money. Watch the barrel. Well, that's pretty serious.
How many noticed that the barrel bent?
Well, I hope we have you convinced that air pressure is not small. Air pressure is a big force. And there's another strange thing about air pressure, and that is that air, when it moves, forgets to have pressure. It's called the Bernoulli effect. Now, the classic demonstration is a little boring, but you put the paper over your fingers like so, let gravity pull the end down, and then if you blow up here a little bit, make this air move, it forgets to have pressure on this side, but you have normal pressure down here, and the paper is lifted up by the Bernoulli effect.
Some would say that is the Bernoulli effect right there.
So moving air forgets to have pressure, quiet air has pressure, pushes the paper up.
You know, I'll bet we could use that in a very, very good way here that would help us out when we are in fact trying to TP somebody's house, for example. What do you think, huh?
Hey, I like it.
So what we do see is we blow across the top of this, and the paper goes up into that lower air pressure thing, and then we just blow it, and there's
And
a
it
tree.
goes up?
Up over the tree.
And you let out a
and
little
paper gun that go way up, way
And we don't
up
have
there.
to throw?
No, not if you know Bernoulli. Here we go. Bernoulli it goes.
All right, I think it'll work. You gotta let the paper out,
Okay.
though.
Whoa, you guys.
What?
I think you got a good idea, and I think it'll
do I.
work. But you need more air.
Need more air. Okay, we can, oh yeah. Oh yeah. This is serious air here, man. What do you think, John? Can you handle that, baby?
I can handle it.
Okay, let's do it. Let's do it. Air blowing across the top of the, okay.
Are you ready,
I'm
Jack?
ready. Are you? Here we go.
Here we go.
There we go. Yeah, TP the house. No problem. Looking good. Yeah. Like that.
Oh, I was going to write that down.
Yeah, I was going to go with it, and I couldn't went out too fast. That's how you do it. That's how you do it.
Now, for the faculty in the audience, this is what's known as relevant education, showing people science, young people science that they can go home and use right away. Now, I want you to shoot a straight air, straight stream, straight up.
Like that?
Straight up. Now, don't do it yet. I'm going to put a beach ball in here, and it's going to push it up in the air, and it'll just set up there.
So it won't roll off to one side?
Well, if it tries to roll off to this side, then there'll be fast air on this side, which doesn't have much pressure, and there'll be slow air out here, and it will push it back to the middle. And if it tries to go off this way, then the fast air will be over here, and the slow air will be over here, and it will push it back to the middle again, so no matter what you do, it'll get stuck.
It's stuck.
Stuck. And then if you tip it a little bit, you might even be able to hang it out there at an angle by blowing over the top of it a little bit.
I want to try it.
All right.
Now remember, we were talking earlier about air pressure, and it's gravity that holds the air down on the earth and gives us this pressure. And we also know from experiments done a few hundred years ago that gravity works on all kinds of things, and even if they're different, it works the same way. So if I were to drop this medicine ball that weighs about 15 pounds and this softball, they'd hit the ground at the same time if I released them at the same time. But then the question came, what if I drop this and at the same time push this out that way? Would they hit the ground at the same time or not? Well, let me try. Let's see if we can do the experiment. I'm going to drop the medicine ball and throw the softball out. Well, you know, that's not a good way to do an experiment because I'm not sure I did it just right. But Jack is up there, and Jack has the right stuff to actually do that experiment.
I've got a device up here that will throw a ball out in that direction. At the same time, it drops one down behind here without moving it forward or backward. So what I'm going to do is hit this little lever up here, and those two will be released at the same time. Now, what you should do to see whether or not they land at the same time is listen for the time when they hit the ground. If you hear it just go bang, then you know they both hit at the same time. If it goes bang, bang, then you know they've hit at different times. So we're going to give it a try. If you'll give me some help, we'll count to 3, and we'll let it go ahead and do it. Are you ready? Hey, was that one bang or what? Yes, it doesn't matter. It doesn't matter if it's going forward or not. It lands at the same time from the same height. That's physics, man, and that's fun stuff.
Well, if we're going to start shooting things, we better have a little better cannon. This cannon shoots these projectiles. And of course, if you shoot a projectile straight up, a cannon straight up, it's not a great idea because you're going to be where the cannonball comes down. But here's how it looks. Fired straight up, but you better be alive because it comes right back down.
Now, if you want it to go the farthest distance you can, the physics tells you you don't shoot it straight up. We've just seen that. You don't shoot it straight out. You shoot it halfway between the two. You shoot it at an angle of about 45 degrees, okay? And that'll get you the maximum range from where the muzzle is to catching it at the same height.
So now I'm at 45 degrees, and we're going to get this projectile to go as far as you can with this cannon.
Right about there. Now, this is the maximum distance. If you change the angle, it shouldn't go any farther than this. If I could get, I have a volunteer over here, Melissa. If you could come right over here. We've never met before, right?
Never.
Okay. Now, she's going to mark the maximum distance. Hank is going to put it at a lower angle. It's going to look like
It's coming straight at Melissa, but it won't reach her. It'll be less. You know why I'm having you mark this distance instead of me?
No.
The university changed insurance companies this year, and they really don't have good coverage anymore.
Now this is 15 degrees too flat. So the projectile really races down there, but it doesn't stay in the air long enough to get the same range. So it's going to fall short. 15 degrees too flat, goes like this, lands about there.
Same height, not as far. Now, one of the curious things is that was a low flat shot. If Hank passes the angle for the maximum range and goes over it, it'll now shoot a big arcing shot, but still come to the same place.
So here's 15 degrees too high. Now, it's odd, but every degree on the opposite side of 45 goes the same distance. So this ought to land right in Dan's bucket because we're 15 degrees too high. Oh, it's a lovely shot. It goes up in the air. It's pretty. But it doesn't go down very fast, so it lands short.
Right about there. About the same place, right, in both cases. Good. Thank you, Melissa.
What you got here is you got your basic poor man's Mercedes. Okay? And what I'm going to do is I'm going to shoot a ball straight up in the air, all right, but it's going to go in that direction at the same time. Because relative to me, it'll stay right straight above me. I'm going to go through the tunnel. I have to get in my machine here. And I'm going to go through the tunnel, and the ball is going to go up and over the tunnel, and I'll catch it on the other side. Because we're both going the same speed in that direction. Okay, Fred, are you ready?
Well, we better test you because Jack's driving isn't so good. So
Well.
we're going to make sure you go through the tunnel.
Okay, here I go through the tunnel. Hello, remember me? I was over there. Yeah. Okay, how am I doing, Fred?
Well, you're driving in a straight line. That's what we need for this.
That's what we need for it, you bet. Now, I can do this. I just know I can. Okay?
Deep breath.
Deep breath.
Here we go.
Now, you know, we've been using some little bitty cannons. I think it's time we need to get out the big stuff, don't y'all? How about this one? Now, for this demonstration, we know that gravity acts on everything, whether it's moving or not, so I'm going to shoot this cannon at Hank when he's at the top of the gantry. But if I do that, as soon as the cannonball leaves the end of the barrel, gravity's going to start pulling it down, and if Hank's lucky, it'll miss him. It'll go underneath him. So how can we make sure that that doesn't happen and I get to hit Hank? The way we're going to do it is at the moment the cannonball leaves the end of the barrel, we're going to drop Hank. I like this one. Now, to make sure that happens, we have a magnet that's powered by the cannon that, you ready, Hank?
Yep.
Is held in place. And I said that whenever the projectile, the cannonball, left the end of the barrel, it was going to drop him, and this is what's going to happen. When it leaves the end of the barrel, there's a switch that drops him. So, that's what we're going to do. So, we're going to put this thing back together. You ready, Hank?
Yes.
Power's on. And to make sure that this is pointed right at Hank, I have a laser that I'm going to have in the end of the barrel, and we're going to shine it right on his baseball glove. And then we know it's pointing straight at him. Okay? And away he goes.
Good.
A little more. It's, hang on. Okay, that's fine. Okay, Hank, can y'all see the laser beam on the back of his glove? Okay, so now we know it's pointed right at him, right? So I'm going to remove the laser pointer. That's out. And the first time I fire the cannon, we're not going to drop him so that you can see what the cannonball looks like as it's flying across the stage, okay?
Now,
Here we go.
If I don't drop, he can't hit me. Because gravity will bend the bullet away from me.
Count of
Below
three.
me.
1, 2, 3. Okay?
Now, the next time he fires it, I'm going to fall. And the bend of the bullet and how much I fall are going to match, so I get to catch the ball. Now, let's say he shoots it faster this next time. If he shoots the bullet really fast, it gets here so quick that I don't fall very far, but it doesn't bend very much. So I just catch it down here a little bit. If he shoots it slow, it takes a long time to get here. I fall a long ways, but it bends a lot, so I catch it down there by the mat. If gravity didn't even work, I wouldn't fall and the ball wouldn't bend. I'd catch it right here. Nothing can go wrong with this demonstration.
Say, Hank, before I shoot the cannon, do you remember the comment you made about my brains coming out of the back of my head? I'd like you to think about that as your life passes. I'm going to arm it.
Yes.
Ready? It's armed. Okay, a little help. On the count of 3. 1, 2, 3.
A moment ago, all of you saw Hank fall on this foam pad up here. And the reason he wasn't hurt when that happened is because the time that he had for the collision was fairly long, and the longer the time gets, the less the force is involved. So if I take something like an egg and throw it up in the air and catch it on a plate, would maybe we expect the egg to break? Yeah, we would, wouldn't we? Because the collision is very, very short. And when the collision is short, the force is big, and it doesn't take much force to break an egg. But what if I'd throw the egg up in the air, put the plate up in the air, pull the plate down ahead of the egg would catch up to the plate, let it touch the plate, and slow it down over. Aha, there was nothing to it. Ah, I know, you want me to let go of the egg. Okay. Now, if I miss the plate, it still illustrates what we want to show, only we have to clean it up. Anybody want it? Yeah.
That was pretty good.
Well,
You see your egg. Whoa, not bad. I can do it higher, though. I can do it way up by the lights.
that remains to be seen.
I'm good.
We'll see. Everyone of us watching?
Now,
Was I
wait a
right?
minute. Wait a minute. Actually, ladies and gentlemen, John is so good at this, catching an egg on a plate, that he can even do it out of this egg slingshot. So now we're going to do it in slow motion so you see how it goes. I'm going to fire the egg and it's going to come through here, and John is going to be running across the stage, and the egg is going to be gaining on the plate, and right about here they're going to be going the same speed, and then the egg will nestle up against the plate, and then John will start to slow it down, and then right here he'll save the egg without even a scratch.
A long collision time, small force.
Okay.
After your performance of the egg and the plate, I'm a bit nervous about this thing.
You should be.
I'll help you.
I'm looking for help.
You betcha. We have here a Swedish airbag. This Swedish airbag will in fact slow down the egg over a long period of time and stop it with no harm done. Be very tough for you to do it because you can't run that fast.
Yeah.
But we can do
I heard
it.
Hank talking about
Yeah.
an egg shampoo a moment ago,
Yes.
and that makes me nervous too.
But here we go. As the egg comes in contact with the sheet, it'll push the sheet backward and
Yeah.
slow it down.
Sorry I'm in your way for some
Over a
of you,
long
but,
period of time.
Try
Here
to
we
look
go.
around me.
Here we go. Are you ready, Hank and Barry?
They think they can save this egg with a silly sheet.
Of course we can.
This egg comes out of here 40 miles an hour.
Or 50.
Or better.
Yeah.
Are you ready?
Yeah. There it is. Aha. Totally unharmed egg. No harm done. Yes. Swedish airbag. Time to stop. Reduces the force.
You know, collisions are pretty interesting things. And if you could run time backwards, rather than seeing collisions, you'd see explosions. And there's some neat things you can do with explosions. One of them is called a rocket. A rocket, the way it's propelled is that you have an explosion where stuff gets thrown out this way and pushes the rocket the other way. I can imitate a rocket with these bags of lead shot, where I can throw them out that way. And in fact, lead shot, anything I want to throw in that direction just makes me go faster in this direction. Now, my limit, my record for doing this, gives me a high speed of less than 30 miles an hour. Okay? So here we go. You ready for this? Here we go. Oh, faster, faster. Everything.
No more clothes.
Okay.
No more clothes.
Remember, I said it was less than 30 miles an hour, right?
A lot less.
Okay. Now, I can do better than that with an apparatus that you see in your schools. Now, often your instructors will tell you that these are fire extinguishers and they're not to be used except in the case of an emergency. And every day after school, your teachers go and put on their rollerblades. They get these rocket assist packs off of the wall and they zoom around the hallways. They've never told you that, have they? Okay, but we're going to show you how to do that. So, now, my friends are going to catch me on the other end, right?
We got it, buddy. We got it.
Okay? Now, I'm going to be going fast this time, so I need your help.
You got it.
Okay.
Lots of help.
Here we go. This could be a little loud.
Uh-huh.
Oh, 1, 2, 3.
Oh. Whoa. Well, I hope he isn't seriously hurt. No, he's not hurt at all. Oh my gosh, we're going to lose that puppy over the edge of the stage. But there's a lady right there who will, oh, okay, this lady. Thank you. Okay. Now, what we have here, you see, is you got your basic beach ball. Now, this is not just any old beach ball. This is a trained beach ball. It will do exactly as I tell it, nothing more, nothing less. For example, I place the beach ball on the table. Watch carefully now. Stay there. See that, huh? Physics is great stuff. Yeah. Well, you know, you people knew that. See, you people already know some physics because you know that if you set something down, it's not going to move, not unless you give it some kind of a force or some kind of a push or pull, because it has mass, and it is, in fact, Newton's first law. Not only that, but if you get it started moving once, it will continue moving unless you act on it with another force. Hank, are you around here? You still, or did you take off?
Right here.
Oh, okay. Why don't you use your head for something useful? That would be good. Now, what I choose to do, what I choose to do is to pop this toward you, and you use your head. He'll use his head to pop it back.
All right.
A force here, a force there.
I can do it.
Here we go, like so. Yeah. Whoa. This is pretty good. You can do better than that, and I can do better than that. There we go, coming right back. Now, if he didn't exert that force on it, it would not stop. It would keep going. Not very much, because this is really a pretty light object, very little mass. But there's I
did it for him, right?
Oh, you want me to? Oh,
Yeah.
absolutely.
Use your head.
You bet. Gonna use the head. Watch this.
Jack is not too bright, you know.
I am too. I was so bright, my mother called me son. Absolutely. That's such an old joke.
Now, of course, the more stuff there is, sometimes we say mass, the harder it is to stop something and then get it restarted. So we're going to see, you've heard of the headless horseman, now we're going to see headless Jack.
No, you're not. I can do this. Yeah. I'm tougher than you are. I'm tougher than that ball is. Not only that, I'm not as stupid as I look. I would never do that because there's too much mass. And when there's that much mass, it could take my head off. I look terrible without my head. I would never do that. This is all, though, remember, this is all physics. This is fun stuff.
You know, it isn't just solids and liquids that have this property, inertia, but gases do as well. This building right now is full of oxygen, nitrogen, various kinds of gases. And I could take a handful of some of these gases and throw it at you people in the audience, but you wouldn't feel anything because gases are so slippery, they'd go around my fingers and fill in behind my hand and nothing would happen. However, if you happen to have one of these giant puffers, which I made in my workshop, they allow you to throw a chunk of gas with the thing and actually see what's happening. Well, not see it, but you can sense it. So I'm going to puff a chunk. Now Hank is lighting a candle. I recently had a birthday party, and I contributed to global warming.
Now we're going to try to blow this candle out by throwing a glob of air at it from that puffer.
Well, that's nice, but it's still irritating because you can't see what's happening. And it would be much nicer if we could see what's happening. Does the air come out like a basketball? Does it come out like a cube? Maybe the letter B.
Maybe.
What? But what if we fill the puffer up with some fog?
Now, John, when I get this full, I don't want you to let any get away before you do it.
I have very large hands, and I can guarantee you that every bit will stay in there.
Okay, I'm ready.
I'm ready
It's
too.
full. All right.
Okay. I hope you're all convinced now what shape it is.
Now there's something that we call friction, and friction does something pretty interesting.
because it sort of holds things together a little bit like glue. So I have these wood blocks that if I push with this claw hammer on one of them, that block will move. If I push on the one down below it, they'll move as a unit. So it makes things stick together, and if I push them just a little bit, they move together. But if I push them real hard, I can make it so that they act independent of each other. I can even, if I can do this, take the one out of the middle. So sometimes friction with a little push makes things all act like one, then other times you can make them look like independent things with a big push.
As luck would have it, we have here a machine that will show the idea that when things are at rest, they tend to stay at rest also. What I have here is your basic a tablecloth. It's not a telephone. It's a basic tablecloth. And if you could get me some dishes there, Hank, that would be good. We'll put that plate right there. We'll take this spoon and put right over here. Let's say I want to eat a lot of soup today, and I have a little glass of wine or Kool-Aid. I'll set that like so. Oh, there it is, the Kool-Aid, yes. Now, I need to look at what I have here.
You know what you got?
What?
The ugliest tablecloth I've ever seen.
That is ugly, isn't it? Now, if I were to eat on that, I'd probably throw up. So what I'm going to do is I'm going to remove that tablecloth from underneath there using the laws of physics, which says that if something is at rest, it stays at rest unless acted on by an outside force. And so I'm going to...
These have mass, too.
They have mass, too. Oh, yeah, water has mass.
Yeah.
So I'm not going to exert any force on the water or the glasses or the dish or anything. I'm going to exert only a force on the tablecloth and remove the tablecloth from underneath. There's another glass you're putting on it. That's enough.
It's the last one.
The last one? Yeah, it better be, because this is sweaty palms time. I could have stuff all over my table, and oh my gosh. This always gives me a little... Now you said that was the last one. That's
the last glass.
The last glass. Okay. Well, I can do this. Because physics doesn't lie. That's another glass. I can see that. That's another glass. You can't. I'm old, but I'm not senile. Now,
I made a mistake.
Yeah, you made a mistake. In a pig's eye, you made a mistake. That's enough. Let's just stop it right there. I can do this. But I got to get pumped up. I got to have it ready. I got to have this going. I'm going to make this happen. I need it pulled nice and even. So I put this wrap around the cloth. Now, don't you try this. Oh my gosh.
Now.
Wow.
You'll either succeed or fail in the first microsecond, because he has to break the friction.
Watch it. He has a buffet. You think I can do this? Yeah. Okay, you think I can do this? All right.
Let's give him a 3 count.
On a count of 3.
1.
I'm not ready. No, I'm just not ready. I'm not afraid. I'm not afraid. My rubber ducky. Now.
One more time.
All right, here we go. Aha! Things at rest tend to stay at rest. Thank you very much. Newton's first law of motion.
Jack, could you give me a little help here? I want to illustrate something about inertia again.
Okay.
Would you sit right there on that stool?
I can do that. I can sit on this stool.
Okay.
All
This
right.
block, Jack, has a
Yes.
lot of inertia.
Yeah, oh, sure it does. It's a
It's
big
at
block.
rest. It wants to stay at rest.
Yes,
and I'd like
I
to
know.
have you bounce this on top of your head.
On my
Could you
head.
do that?
On my head. Okay. All
Oh,
right.
boy,
we'll
I'm glad
do
you-
that. Okay.
Now,
Now then.
it's at rest. It wants to stay at rest.
Okay.
I'm going to try and drive a nail in this.
Shut up. Are you really? This is crazy. Okay. Oh. Well, that's no big deal. That worked
Now,
easy.
the reason you weren't hurt, Jack, is
Yeah.
this has so much inertia that it doesn't want to move.
Yeah. it does.
Remember when we first started this, I took a $1 bill and
Yeah.
put on your head. And then we had to quit that one for a while.
Didn't work at all. Called me Spike for weeks after that. Yeah, that was terrible.
Lots of mass, lots of inertia. It won't go anywhere. That's what saved you this time.
It did indeed. Thank you much.
Now, this is a bed of nails. And these are real nails. In fact, some students at Jack's High School built this because they were interested in how it is that people can actually lie down on a bed of nails, and I will lie down on this for you in just a minute. But one of the things you never do if you have a bed of nails is jump into bed. Because once you're in motion, you tend to stay in motion. So here's a potato playing the role of someone jumping into a bed of nails. We're going to do it sideways so you can see how it looks. But this is how it turns out. It's not a good thing. In fact, the word is impaled. And now there's holes all over the place in the spud, and there's water or juices, spud juices running out. Now, if you do it, it's the same result, but it is more colorful. But the outcome is the same. On the other hand, if I place the spud gently on the nails, it's okay because it doesn't rest on a single nail, it rests on many nails. Each nail holds up some of the weight of the spud, and no nail is so hard against the spud or so much pressure that it pierces even the thin skin of the spud. And it turns out, of course, that humans can actually withstand a lot more pressure on their hide than you might think, several pounds, in fact. So, if I don't jump on the nails, and there is enough nails, then they'll hold up my weight without any nail hurting too much.
Boy, and that's a lot of weight.
All right, so now I've got my head up, my feet up, so that all my weight is on the nails, and I'm not saying it's comfortable, but I don't think I'm bleeding yet.
Let's hear it for Hank, huh? Now, his weight is spread over many nails. I can even add more weight to him, and it still doesn't bother him too much. And in fact, because this concrete block has so much mass, I can actually hit on it with something like a sledgehammer, still won't bother Hank. In fact, I can hit it so hard with the sledgehammer, I can break it. Okay? Here we go. Woohoo!
No harm done.
It's physics, you guys.
It's just physics!
So let's do it.
Let's see
No
here.
blood,
Oh, look at that.
No blood.
No holes.
no blood.
Ish.
Now, for just one moment, I want to talk to all the faculty in the audience. The United States, and Minnesota is no exception, is rather physics phobic. People seem to be afraid of physics. They think that physics is just for nerds and special people. But it's not. Physics is actually quite interesting, it's actually understandable, and it can even be fun. So now, the faculty, I want you to chant with me. Physics is interesting, understandable, and fun. And if any of you other students would like to join in, that'd be good too. Here we go. Physics is interesting. Uh-oh.
Let's hear
Do it again.
Follow me. Interesting, understandable, and fun. Right.
Listen, we've enjoyed the hour we spent with y'all, and we hope y'all enjoyed it and that you learned something along the way. Thank you very much for being
Thank you
here
guys.
today.
Thanks for coming out. Wonderful time. Thanks a lot.